Welcome to Honors Pre-Calculus Day 1. We're going to start with two words you might have seen before, domain and range, specifically the domain and range of a function. The written definitions of these two terms that we're going to use are the set of all x values that define a function for domain and the set of all y values that define a function for range. One way to tell them apart is the domain is the set of all input values and the range is the set of all output values. Paired with these terms, the set of all input values, these are independent, and for output they are dependent. Now they're dependent on these independent variables. So you plug in the input values and they give you the output values. So it's the set of all x values for domain and it's the set of all y values for range. Now we're going to look at these two terms with regard to 9 parent graphs. So these are going to be baseline graphs we're going to use to transform into others. These are really important structures, really important shapes that you need to know. And the fail-safe for graphing is you can always plot points. One at a time you can plot points, but there are faster, more accurate ways that give you more powerful tools. But you can always make a table. So if you were to make a table of values, you have your input values right here, and you need to fill in the output values. So you're plugging in -3 into x where it says x squared and then -2 and so forth. So if you fill in this table, you end up with these values. So when you plug in -3, you get 9. So at -3, there's the point -3, 9, -3, 9. There's the point -2, 4, and so forth. So this function obviously extends in either direction. It's a parabola facing up. So what about the domain? What's the set of all input values? Well, is there anything x can't be? Are there any numbers you can't plug in? No. So the set of all real numbers is denoted r with this 2-bar r. Another way to write it is in set notation, -infinity to infinity. Now, it's not really accurate to say to infinity. Infinity is a concept. What about the range? What does the output cover? Can the output ever not be something? Well, look at the lowest value it can be. The lowest value it can be is right down here where y is 0. So the range is above 0 and including 0. So in this case, the range is going to be all real numbers greater than or equal to 0. Another way to say that is including 0 and going upwards towards infinity. When you square something, it's always going to be positive. So let's look at the cubic function. So we can do the same thing if we don't remember it, and you can fill in this chart, and you get an S-curve facing up. It's pretty cool. It does extend. It kept on going here. Now, what's the domain here? Is there anything that x can't be? Well, again, no. So you could write it as all real numbers, and another way is -infinity, infinity. You know, I like the specificity of set notation, but all real numbers, it's really nice to be able to write that, and you can totally do that. Now, what about the range? Meaning, what part of the y-axis is covered by the outputs? Is there any output that you can't get? Well, in this case, it goes negative and positive, and it covers all of the possible real numbers going up and down. So in this case, the domain and range are the same. You end up with the same thing for domain and range, all real numbers. Now, what about the function 1 over x? Well, we can do the same thing and fill in all of these values. So let's do that. And you end up with a pretty interesting graph. There is symmetry here. You get this nice curve extending. So remember, it does keep on extending. So let's take a look at this. What's going on here? Well, let's look at where there's some issues. Well, something's going on at y equals 0, which is right here, and something at x equals 0. So what's going on at x equals 0? Well, x can't be 0 here. You can't plug in 0 into the denominator because then you would be dividing by 0. What's going on is that there are asymptotes at each of these, at the axes. Y equals 0, the x-axis, and x equals 0, the y-axis. So if you were to come up with the domain, what's the only thing x can't be? What's the illegal operation? You can't divide by 0. So in this case, it's all real numbers except, and I'll go back to red here, all real numbers except for 0. Can't be 0. Another way to say this, again, with set notation, it's all the way up to and not including 0, and then union 0 infinity. That just means all real numbers except for 0. You could also write out that sentence. That's totally fine. Now, looking at the range here, what's the only thing you can't get out? Meaning, what's the only output that you can't get out? Well, you can't touch the x-axis, which is when y equals 0. So in this case, the range is the same. You can kind of see how this is similar. If you turn your head to the right, you end up with the same shape. So in this case, the domain and range are the same. You can't plug in 0, and you can't get out 0. So what about this nice curve right here? The square root of x, we're going to do the exact same thing. And we're going to note that you can't plug in a negative number. I say you can't, it's just not defined with real numbers. The square root of a negative number is imaginary, so if we're just dealing with real numbers, in this case, this graph just keeps on going this way, but it stops right here because we're just dealing with, it stops right there at the origin because we're just dealing with real numbers. So in this case, the domain is going to be R, if you want to say this, all real numbers greater than or equal to 0. Another way to say that is 0, infinity. Now in this case, if you look at the range, meaning what are the output values? Well, you can only get positive numbers. You can only get positive numbers on this. So again, it's R greater than or equal to 0, 0, infinity. So next we have 2 to the x and then 0.5 to the x. And if you fill these in, you end up with two graphs that are pretty similar, but one grows and then one decays. Quick reminder that something like 2 to the negative 2 means 1 over 2 squared. So when you fill this in, you end up something that starts pretty small and gets larger. So if you plot this out, you end up with this nice curve. Now you'll notice that you do have an asymptote here. Here's the asymptote, also known as the x-axis. You can't touch it. Are there any numbers you can't plug in? We can actually plug in everything. If you plug in 0, remember 2 to the 0 is 1. So you end up with the domain being all real numbers because there's no restriction. You can plug any real number in. Now what about the range? Well, you can't get any outputs less than 0. So you end up with the range being greater than 0. Keep in mind you can't make this equal 0. 2 to the x can never equal 0. No matter what you plug in, you can't make it equal 0. So it's going to be strictly greater than 0. Another way to write that would be 0, infinity, with the open bracket right there, not the closed bracket. Now with this one, you get something very, very similar, just goes the opposite direction. And just some algebra here, 0.5 to the negative 4, that's the same thing as 1/2 to the negative 4, which is the same as 1 over 2 to the negative 4, which is equal to 1 over 2 to the 4, which is equal to 1 times, put that times somewhere else, 1 times 2 to the 4th over 1, 16. That's just a long way of saying that this whole thing turns out to be 16 right there. Now if you do similar work, you can fill in the rest of the chart. And you'll notice that the values are very similar and it decays. Well, in this case, the domain is the same. It's going to be all real numbers for the domain, and the range, it just has to be greater than 0. And again, I'll leave it as set notation. It's kind of a nice, clean way of writing it. Let's talk about logs. In this case, log with no base written in, and log with no base written in means log base 10 of x. That's the default base. It's the base we count in. Now, you might remember that the log of a negative number is undefined, and that the log of 0 is also undefined. The definition of logarithm is something you should definitely look up, but one thing you can remember is it's the same thing as saying log base a of b equals x is the same thing as a to the x equals b. So you could use your calculator, you can remember this, but with base 10, these are numbers you should be able to work with in logarithms. So if you fill this in, you end up with those numbers right there. Part of how the Richter scale works. It's a great way of measuring things that change very, very quickly. So when you plot these, you end up with a curve like this. So what do you see there? Well, I see one asymptote here. You can never be 0. You can't touch it. You also can't be to the left because there's left of the y-axis, because you can't plug in negative numbers into the x value of the log right there. So the domain in this case can't be 0 and it goes positive. What about the range? Well, this is slowly getting really big. It slowly get as big as you want. So if you plug in a big X, you get a smaller Y, but it's still, you can make Y as big as you want. You can make Y as big as you want. And this also goes down. So what do you end up with? What part of the Y-axis is covered here? What shadow would it make if you were shining a light from the right? Well, it is indeed all real numbers. This is the fun absolute value function, which you might remember means the distance from the origin. So if you fill this one in, you end up with really two functions being glued together. You have the first function here, and you have the second function here. And then you get to decide which one is at the origin. So how do you go about filling this in? Well, the function is equal to negative x when x is less than 0, and it's equal to x when x is greater than or equal to 0. So you can flip this, but just when I say flip this, the equal sign right here, this equal sign right here can be either there or below. You just can't be in both. So in this case, what's the domain? Are there any x values you can't plug in? Well, no, there aren't any. There's no dividing and there's no square root. So in this case, the domain is all real numbers, but you'll notice that the range only goes up. It only covers the positive y values, but it includes 0. So you'd write it like that, or you could say r is greater than or equal to 0. My preference is this notation, the set notation, and also it's very important that you remember the hard bracket on the 0 right here, because that means it includes the 0. So this is a really cool function, int x. This is the function outputs, this function outputs the largest integer less than or equal to the input value. Less than or equal to the input value, less than. So when you do this, you have to do this really carefully. So like if you plugged in 0, you'd end up with 0. And because the largest integer less than or equal to. So you have to do this very, very carefully. So if you fill this in, you end up with, kind of think of it as the hard round down. You cut off everything after the decimal. Now, the key thing is to realize that it's going to be an open dot at each of the whole integers. Because you get infinitely close to 1, it's still going to round down in this int function to 0. But then 1 will stay at 1. So when you graph this, it looks like this right here, because every value up to but not including the integer goes down. So 0 all the way up to 0.9999 goes down to 0, but then once you get to 1, it jumps up to the 1 value. 1.99999 stays at 1, but then once it gets to 2, it jumps to 2, and that same pattern repeats itself. So the way you can write this as a piecewise function is, remember, it's going to be a lot of piecewise functions, but if you look at the center here, it's going to equal to -2 when x is between -2 and -1, but not including -1. And then it'll be equal to -1 when x is between -1 and 0. And then it'll be equal to 0. Pattern continues when x is between 0 and 1. Now you remember, you read these by starting in the center. X is greater than or equal to 0 and strictly less than 1. You could keep on writing these, but remember the dots keep going here. So it's equal to 1 when x is greater than or equal to 1 and less than 2. And it's equal to 2 when x is greater than or equal to 2 and less than 3. These are and statements. Start reading them from the middle. Now one of the fun things here is, what's the domain? Are there any x values you can't plug in? No. You can find an output for any input you plug in, and the inputs are not restricted. What about the range, though? What do you have to write here? Well, you could list it, but it really is just simply the integers. When in doubt, you can write a sentence or write the description. It is the integers. And fun fact, you can write integers as a cool double bar z. You'll use that a lot in future math classes. So we're going to use these base functions and transform them. So our base function is going to be called f here. So that's the function f of x, and there are 3 different letters, 3 different places we can modify what's going on, with a, with c, and with d right here. So for a, that's where you start. What does a do? A, it's a vertical stretch by a factor of a, and if a is less than 0, it flips the entire graph over the x-axis. Next, let's look at the C value. And the C value is going to shift things left or right. The way I remember this is to think of it as the opposite. If C is greater than 0, it goes left that many units. And if C is less than 0, it goes right that many units. It's kind of the opposite. And then what about D? This is up and down. And this is what you think it would be logically. If D is greater than 0, you go up. And if D is less than 0, you go down. So let's take a look at these right here. So we're going to graph each of these without a calculator, state the domain, and then you can use a calculator to check it. But what's the base function for this one? The base function for this is the absolute value of x. What does that look like? Well, if you graph it out, you end up with the absolute value of x right there. Okay, it's that nice upward facing v. Now, what does this -3 do? Well, that stretches it vertically by a factor of 3, and because it's negative, it flips it over. So that first transformation means it's going to flip it over and stretch it by a factor of 3. So all the y values get multiplied by 3, and then you can flip it over. So what does this mean? With just -3x absolute value, you end up with an upside down v that's 3 times as steep. But then what does that 2 on the inside do? Well, that 2 on the inside, it moves it 2 to the left. It moves it 2 to the left. So you end up with the same shape, but 2 to the left from the +2. And then the last thing is this up 4. It goes up 4. So you end up with a final graph just like this. It goes like this. So here, here, here. So the black is the final. So remember, the green is -3 times x plus +2. And then the black is simply the final x plus 2 plus 4. Now it's the same work regardless of the base function. What's the base function for here? The base function for this next one is x cubed. And then what does this -1 do? It's 1 right, and this is 2 down. So the base function, remember, 1 cubed is 1, 2 cubed is 8, 3 cubed is 8, sorry, 3 cubed is 27, so it's up here a lot. So you end up with this as your base graph, like so. And then you just move it 1 to the right and 2 down. 1 to the right and 2 down. 1 to the right and 2 down. So it's the same shape, but now it's centered around here. So you end up with this graph. You like my curve? It's pretty good. So let's go back and fill in the domain and range for each of these. Well, the absolute value of x by itself, the domain was all real numbers. And if you move it around, it's still going to be all real numbers. Now, for the range, for this final graph, look at the black one here. Look at the black one in the center here. What's the highest y value? Well, the highest y value is 4, and it only goes down. So the range has to be less than or equal to 4. Another way to say that is -infinity all the way up to 4. And it's also inclusive of 4. Now for the cube function over here, is there anything you can't plug in? Nope, you can plug in everything. So it's going to be all real numbers. And is there any output you can't get? Nope, you get all of it.